So in chapter 17, we're taking a look at acids and bases. And so let's start with a little bit about what acids are. So the nature of acids, right? The structure of acids and their properties. Most of you remember from general chemistry that acids have hydrogen associated with them. For binary acids, this is an example, hydrochloric acid, example of a binary acid. The hydrogen is attached directly to the other atom. But in oxoacids, predominantly, it's the hydrogen attached to one of the oxygens attached to a central atom. And there's also other kinds of acids. We'll talk about those definitions as we move along through this section. One of the things we know about acids is that they're sour if you taste them. Of course, that's the first thing you're not supposed to do. They dissolve metals, they can neutralize bases, and if you're not familiar with litmus paper is a paper that's created out of a plant pigment, and it turns red when it is in an acidic solution. I also want to point out organic acids. Organic acids have this structure. This is known as a carboxylic acid. This is by far the most common acid structure in organic chemistry, so I thought it would be worth showing. Vinegar is acetic acid, and if you remember that one, we always write it as HC2H3O2, but in fact, what acetic acid is it's actually this same structure with a methyl group, a CH3 group, on the carbon instead of, I just drew a blank over on this side, right? I didn't put anything here. But this would be, for example, acetic acid. Again, it's a type of oxoacid, so the hydrogen is attached to the oxygen. If you're curious, there's a lot of these kinds of acids. For example, you've heard of lactic acid. When you work out, you build up lactic acid. That's actually just this. Again, a carboxylic acid functional group like this, and then an OH group here. So that's actually lactic acids that builds up in your muscles as you work out. Again, it's a carboxylic acid, and the only part that's really different is this other end of the molecule. And you can also have, for example, dicarboxylic acids. Example would be like tartaric acid, which we get from grapes. And anyways, there's a whole bunch of these different kinds of organic acids. Let's talk a little bit about bases. So usually when you're introduced to acids and bases in general chemistry, the first thing that you learn about bases is that they all have this OH group on it. So for example, NaOH, right? But I've underlined the OH here. That's a hydroxide. It's also important that you recognize that this is a metal ion. And so metal hydroxides can generally perform the function of bases. And one of the first things you learn about bases is that they will release or produce OH minus in solution. But it turns out that's not the only way that solutions can be made basic. One is the addition of ammonia, and one of the things we'll learn in this chapter is how these molecules like ammonia, the nitrogen in particular with the lone pair on top of it, can provide a situation where a solution can be made basic. Now, in terms of properties, they're typically bitter. Many of the natural toxins known as alkaloids are bases, and so when you taste poisons, they tend to have this bitter flavor. Our body sort of has evolved this sense of this is not good for us, and so we seem to reject that stuff. But yes, bases are bitter. They also have a slippery feel in it, and we'll learn about this a little bit in the upcoming chapters. But that mostly is because it removes metal ions from the solution that cause water hardness. And so, anyways, bases tend to have this slippery feel to them. They neutralize acids, which is, the opposite of metals that neutralize bases. So they undergo neutralization reactions with each other, and they turn litmus paper blue. So litmus paper is a great way to quickly indicate whether a solution is acidic or basic. Now, what we view as a base depends on how we define acids and bases. And so what we're going to do next is look at some acid-base definitions. Okay, so there are basically three. I hate this chapter because I like to say basically a lot, but anyways, basically there's three different definitions of acids and bases that are common. The Arrhenius definition is the one you first learned from general chemistry, and basically, uh, acids have hydrogen, right, and bases have hydroxide. And really, the Arrhenius definition is based on what's formed in solution. That is, do you form hydronium ions, H plus, or do you form hydroxide ions? Now, that's the definition you're probably most familiar with. Then there's Brønsted-Lowry. Now, Brønsted-Lowry is based on the idea of proton transfer. So what exactly is a proton, right? Well, remember, hydrogen only has one electron. So when we're thinking about hydrogen ions like H+, in a sense, that's just a proton that's transferring. So when we look at proton transfer reactions, that opens up a whole wide range of bases, it turns out, and acids that Arrhenius definition doesn't cover. And then there's Lewis theory, which is really about movements of electrons. And it turns out this is the most general of the theories. But one of the things I wanted to point out is Arrhenius is the simplest theory. Brønsted-Lowry covers more definitions. And then Lewis theory covers even more definitions of what can be considered as an acid or a base. So, the Arrhenius idea, right? Arrhenius acid produces hydrogen ions in water. So for example, this would be a definition of an Arrhenius acid that you might be familiar with in Chem 1A. But you might also be familiar with a second idea, is that this hydrogen ion is extremely unstable because of its positive charge, so really can't exist as an ion by itself in water. The result is hydrogen ion reacts with a water molecule and produces hydronium ion. And again, I'll write this out because probably haven't thought about this in a while. Hydronium ion. Overall, if you add these two reactions together, you'll notice that you can cross these out, and what you'll end up with is HCl plus H2O makes Cl minus plus hydronium ion. And so this is the way, this sort of definition is the way we're going to look at acid-base reactions mostly in this chapter when we're talking about adding an acid to water. Now, an Arrhenius base produces hydroxide ions in water. So sodium hydroxide, for example, will dissociate into, because it's an ionic compound, dissociates into sodium ions and hydroxide ions. And other than that, that's all really the Arrhenius theory gets to cover, because it really is dependent on having OH in the structure. So when an acid and a base react with each other, that's known as a neutralization reaction. And the products, when we're looking at the Arrhenius definition at least, the products are always water and a salt. The technical name for the ionic compound that's produced from an acid-base reaction is a salt. The hydrogen in the water comes from the hydrogen in the acid, one of the hydrogens does, and then the OH group comes from the OH of the base. Again, metal is what the M stands for, so this is a metal hydroxide plus, right, an acid produces water and a salt. So let's go ahead and write one. And this is going to be for the complete neutralization, because I wanted to show you some tricks and stuff for balancing and for writing products for these reactions. So first, when you're going to be doing these problems, it would be worth reviewing acid nomenclature rules and rules for naming ionic compounds from your Gen Chem stuff. But hydrochloric acid would be HCl. And then magnesium hydroxide would just be the magnesium ion, which if you look on the periodic table, that's group 2, so that's Mg2+. And hydroxide is OH minus, so to make a compound out of them, you need 2 OH minuses to go with every magnesium, so I'll write that here. And then you're going to do an acid-base reaction. Now, look back at this reaction. One hydrogen for every hydroxide, right, to form a water. That's how these things have to react. So if we do a complete neutralization, I need to have a hydrogen for every hydroxide. Now, you know, notice magnesium hydroxide has two, right? It's two OH groups. So what that means is it's going to take me two HCl's to react with it, and I'll get two waters out of it. So you see how easy that was, just recognizing the type of reaction that it is and the rules that apply to acid-base reactions of having to form water. I just look to see the number of hydroxides that are here, and that's how many HCl's I'll need. Now, the other product would be the salt created from magnesium and chloride. And again, magnesium's 2+, chloride's 1-, so you could write the product as MgCl2, and that would be the balanced reaction for the neutralization of HCl with magnesium hydroxide. Now, the same kind of thinking applies to polyprotic acids. Polyprotic acids are the same, follow the same pattern, except that they have two hydrogens on them. So, for example, sulfuric acid, H2SO4. And let's say you reacted that with NaOH. Well, before you even get started, you recognize that this is two hydrogens, and so you'll need two sodium hydroxides to go with that to form the two waters. So you know you're going to be getting two waters out of here. And there's going to be a 2 here because I needed two hydroxides for the two H pluses, and then I can write the other product, and that would end up being sodium sulfate like this. And that would be the balanced chemical reaction for the complete neutralization of sulfuric acid with sodium hydroxide. So just a couple of easy things to make this part of the class, go a little smoother, is just remembering how to write the reactants and products and how to balance them quickly for acid-base reactions. Now, the Arrhenius theory is a good theory. It gives us a good foundation for what's acidic and what's basic, but it only works in water, and it has a problem where hydroxide is the only base in neutralization reactions, but there are actually lots of different amine type substances that we were talking about earlier that can make solutions basic, and so this is sort of the immediate need for a different definition, and this is the Brønsted-Lowry definition. And so in the Brønsted-Lowry definition, an acid is a proton donor. So that means it's going to give up a hydrogen. And really a hydrogen ion in a proton transfer reaction, which means in order to be called an acid in the Brønsted-Lowry definition, it has to be part of a reaction. And the base is the thing that accepts the protons in the proton transfer reaction. And again, by proton, we're simply meaning H+, right? So let's look at an example of an acid-base reaction using the Brønsted-Lowry definition. So here we have HCl, which is going to be my acid, and I'll show you why I know that in a second, and NH3 goes to Cl- and NH4+. So the acid is the proton donor. So you'll notice HCl over here, and then it's Cl- here. So this must be the acid. And that means if the HCl, because it donated the hydrogen, right, is the acid, the NH3 must have accepted it. And if you look at the formula for NH3 here, there are 3 hydrogens, and then over here, the ammonium has 4 hydrogens. So this is the base. So my acid is HCl, my base is NH3, and then we talk about what's called the conjugate acid and conjugate base. And so in a lot of these reactions, what we usually consider is that these could be equilibrium reactions. That is, there's a forward reaction and a reverse reaction. Now, if you're looking from the product side and going towards the reactants, right? So you're thinking of it like this. I have a Cl- plus an NH4+ going to an HCl plus an NH3. What's the acid in that reaction? Well, whatever donates the proton is the acid. So this would be the acid, and then this would have to be the base. And then I have the products of those on the right-hand side. So rather than making it confusing, because it already is a little confusing, by having two different acids listed, we talk about the acid and its conjugate base. And this is Cl- is the conjugate base of the HCl. So the conjugate base would be Cl-, and then the conjugate acid, because it behaves as an acid in the back reaction. This is known as the conjugate acid, NH3, NH4+. Now, we also define things like conjugate acid-base pairs, and so a conjugate acid-base pair, one would be HCl and Cl-, like that. The acid form and its conjugate base form. The conjugate acid base form for the second one would be NH3 and NH4+. And you can always tell which one's the acid because it has hydrogen or it has more hydrogen. Okay. So conjugate acid-base pairs, there will always be two pairs, 4 compounds, in every acid-base reaction when we're looking at the Lewis or the Brønsted-Lowry definition. Okay, so summarize, the acid gives up the proton, the base accepts it, right? And then what the acid produces is known as its conjugate base, and what the base produces is known as its conjugate acid. So what I want you to do on these two slides is label the conjugate acid-base pairs. So we're going to go like this. A is going to be for acid, and B is going to be for base. And then we'll add a C in front of it, and that'll be for conjugate. Okay, so like I did here in this particular one, I wrote conjugate base for the Cl-, and this would be the Ca, the conjugate acid for ammonia. So I'll give it a second so you can pause, and I'll just label them all quickly, and then we'll discuss. Okay, so there's the answers. Ammonium gave up the proton, become ammonia, so this is my acid, and then water's my base. And then the conjugate base comes from the ammonia, and the conjugate acid in this case is hydronium, which is a very common conjugate acid to see in a reaction. Okay, the bottom one, I have cyanide ion. Cyanide is clearly the base because it picks up a hydrogen. So instead of looking at what lost the hydrogen, I looked at cyanide picking up the hydrogen to form hydrocyanic acid, and then that means the acid must have been water, and then the conjugate base is hydroxide in this case. And this is how, by the way, Brønsted-Lowry theory is different. This is one of the main ways it's different than Arrhenius theory, is that I produced OH- through a reaction that didn't involve a metal hydroxide. Okay, so what's kind of weird about these two reactions if we take a close look at them, right? Look at water in both of the reactions. And in the top one, water is a base, and in the bottom one, water is an acid. And it's important to understand that in Brønsted-Lowry theory, that there are many species that can be both an acid and a base. I'll give you a quick idea how to identify them in a second. So it's not unusual to see that in the case of water. Now, if we look at these compounds in general, these are known, what are known as amphoteric substances. That is, they can act as an acid or a base. And it turns out even water can act as an acid and a base by itself in one reaction, and that's this reaction here. This is known as the self-ionization reaction for water. It's a very important equilibrium, actually, and we'll spend a little bit of time on this, but two water molecules get together. One of them acts as the acid and donates a hydrogen to the oxygen of the other. So that means this is the base. So this is the conjugate acid, and this is the conjugate base of the reaction. Now, how do you recognize amphoteric substances in general? The most common ones are ones that are part of polyprotic acids. So, for example, I just gave you an idea here. If I have H3PO4, well, H3PO4 can only be an acid, it turns out, but H2PO4 minus, which comes from, is the conjugate base, right, of phosphoric acid, can either lose a proton going this way and forming HPO4 2 minus, right? Or it could go back this way. And so any of these intermediate stages, right, of a polyprotic acid are considered to be amphoteric. That is, they can either accept or donate protons.